contribution of Poincaré and later Klein on the question of uniformization. So let me remind you or state what Poincaré was aiming at. So the way we formulate it today is this. So the theorem in the modern terminology is this. You have X, a compact Riemann surface, let's say of genus 2 or more, and then the theorem says then the universal cover of X is the Poincaré disk. Or another way of stating it is X is the quotient of the disk by some discrete subgroup in the group of biholomorphisms of the disk or isometry of the Poincaré metric, which, as you know, is PSL2R. Okay, so before I go on, let me make some comments on this statement that Poincaré could never had mentioned this way. He could not think this way because of many reasons. One is this. The concept of universal cover was totally unknown in 1880. So this is 1882. In 1882, it was totally beyond the preoccupation of mathematicians to take a space and think of its universal cover. It was not belonging to their culture. And even more complicated, but this will be discovered later, in 1889, and then in the papers on analysis situs of Poincaré much later, beginning of the 20th century, this concept will be explicitly formulated. But this is even more complicated. Poincaré never mentioned the concept of quotient. Taking a disk with a group action, take the quotient space, was outside of their understanding. He never mentioned that, even later. And it is amazing because Poincaré is dealing with groups acting on a disk. He's looking at fundamental domains, etc., etc. I will discuss that in a moment. But never he will say, let us consider the quotient space. And recently I was asking Jean-Pierre Serre about this concept. You have a group acting on a space, and we take the quotient. When was this clear in the mind of mathematicians? And the answer of Jean-Pierre Serre was rather interesting. He said that he considers that this is one of the main contributions of Bourbaki. It's rather, it's very recent concept. So Serre told me that when he was young, so a long time ago, but anyway, in let's say in the 50s or something, he went to his advisor, Henri Cartan, and he said, Mr. Cartan, what is the quotient of the space by a group action? And Cartan said, well, I don't know, it's too complicated. Because for the definition that we have for us, the definition you have an equivalence relation, and we take equivalence classes, and we think of each equivalence class as being a point of a space, and we define a topology on the quotient space. This was totally non-natural to people at the time. So Serre told me that Cartan told him, well, if you want to take a quotient space, you take a fundamental domain and you glue the boundaries. So at the time, it was totally non-natural to take a quotient. So this statement would have been impossible in the terminology of Poincaré. Poincaré was not discussing quotients. So what I want to do today is to try to state the theorem the way Poincaré was stating it, and you will see that it's, of course, equivalent to this, but it was not expressed in the same way. So first, what is the contribution of Poincaré? At first, in 1881, Poincaré had no idea that something like that could be true. He was just looking at examples. So the strategy of Poincaré at the time, he was not dreaming of that. The strategy was that, one, to construct many examples of discrete subgroups of PSL2R. And two, instead of looking at the quotient of the disk by these examples, he looks for functions on the disk which are invariant under the group. For him, it's very explicitly mentioned. He wants to find something analogous to the theory of elliptic functions. An elliptic function is a meromorphic function in the plane which is invariant under translations. And again, if you look at the history of elliptic functions, elliptic curves, it took a long time before people dared taking the quotient of the plane by the lattice. They were only looking at functions on the plane invariant by translations, which of course for us is the same. But for them, it was not the same. So what Poincaré does, he constructs functions f on the disk with value in C union infinity, which are meromorphic and which are invariant under the group. For every gamma in gamma. Okay, so he does that. I will explain that. And three, he proves that in our modern terminology, that this quotient is an algebraic curve. But in the terminology of Poincaré, the theorem is this. If you take two functions like that, for any f and g which are invariant like that under gamma, there is a polynomial in two variables such that P of f and g is identically 0. So what he does is that he looks at the field of functions which are invariant under the group. And what he does is that he shows that this field has transcendental dimension 1. Which means that if you take any two elements in this field, they are connected by some polynomial equation. So somehow he says that the group gamma, so it's explicitly mentioned, there is some kind of dictionary between the group gamma and the algebraic curve P is equal to 0. Of course, if you change f and g, you get a different algebraic curve, but the curves that you get are birationally equivalent in the sense of Riemann. So what really he gets is a map from groups going to the set of algebraic curves up to birational equivalence. Which is precisely what Riemann was looking at. So this is a construction going from groups to curves. But at first, again, Poincaré was not dreaming of that. He was just making examples of groups. Examples of groups, and hence examples of algebraic curves, which are described by a group. So he was happy because he had many examples, depending on many parameters. And then began the conversation or interaction, competition, collaboration with Felix Klein. I think I told you already that Poincaré was not really aware of the work of Riemann, so he knew almost nothing about the work of Riemann. But in this exchange of letters between Poincaré and Klein, both of them at the same time discovered that on the left-hand side, you have some flexibility. The groups depend on some parameters. On the right-hand side, Riemann had counted the dimension of the space of Riemann surfaces of a given genus, and Riemann had found a dimension 3g minus 3 dimensions over the complex numbers. And if you count roughly the number of parameters that you have on the left-hand side, you find 6g minus 6 real parameters. So both of them, Riemann and Klein, understand simultaneously that the space on the left and the space on the right have the same dimension. It was like a great surprise. I must say that even for me today, it's like a miracle. I mean, I'll discuss that later. It's not clear to me that it should be the same dimension, because these two dimensions come from very different computation. I'll discuss that maybe in some next lesson. It's like a miracle that 6g minus c is twice 3g minus 3. So you have these two sets of the same dimension, and it's rather easy to prove that this map here is injective. This is proved completely, explicitly, and independently by Felix Klein and Poincaré. Of course, both of them know that some maps could be injective without being bijective from a manifold to a manifold of the same dimension. Then you have to do something to prove that this is indeed a bijection. And you basically, in modern terminology, you have to prove it's a proper map. And then both of them understand the difficulty, and they start on a big competition to prove that this map is proper. And I must say, and we looked at the original papers of Klein, Poincaré. Poincaré wrote long papers on the question, maybe 200 pages proof, trying to see that when you go to infinity on the left, you go to infinity on the right. Klein also has a long paper, which is even more complicated. It's written in German. It's a long paper proving basically the same things. But we decided, the group of co-authors, we decided that none of the proofs are convincing. So it turned out after this big competition, both Klein and Poincaré considered that they had a proof. Each one considered that the other one had good proof. But I think it's totally nonsense. What is true is that they did understand the difficulty. They did understand that one had to prove properness. Poincaré did understand that, did guess what is the meaning of to go to infinity, as we say today in Teichmüller theory. He did understand what this means to go to infinity in the moduli space, in what we say today the Deligne-Mumford compactification. So they understood. They understood the problem. They did some things, but they did not prove the complete thing. Anyway, so putting this together, at the end, maybe I should put here Poincaré and Klein, or Klein and Poincaré. At the end of 1882, they were convinced that they had proved that. So what I want to do today is to tell you about the beginning of the story, and what my aim, my goal would be to give you, in the book, we took these ideas of Poincaré and Klein. This is called the continuity method. I told you we are not convinced by the proof of Poincaré and Klein, but we tried to make it correct with modern terminology, with modern tools. And we did it. So in the book there is a proof that this is doable. Of course, we are using tools that were Poincaré and Koebe and Klein did not know, like quasi-conformal maps or things like that. It did not belong to the package of Poincaré and Klein. But anyway, it's possible to restore this idea and to prove the theorem in this case. And what I want to do, not today, but to start probably next Wednesday, I want to give you an idea of how one could fix the non-correct proof of Poincaré and Klein. Okay, so maybe I should say also a few words. Such a function f, which is invariant under such a group, is called a Fuchsian function. And here there is also a complicated story. As I told you, Poincaré, when he started working on this question, first of all, was totally unaware of Riemann, Schwarz, Klein, all these people. The only thing he knew came from a paper by Fuchs. Fuchs had written a paper on linear second-order differential equations in the complex domain. This paper was, of course, written in German, but for Poincaré it was not a problem because Poincaré was fluent in German. He was born in Nancy. He spoke fluently German, but his advisor, the advisor of Fuchs, the advisor of Poincaré, was Hermite. Hermite was really interested in differential equations, but Hermite could not understand a word of German. So he was happy to have a good student knowing German, and Hermite asked Poincaré to read the paper of Fuchs on linear differential equations. And Poincaré read it, understood it, and more importantly, understood that the paper was completely wrong. It was really, it's interesting to how is it possible to write such a wrong paper. Anyway, looking at this wrong paper of Fuchs, Poincaré was really interested by the subject and created all this theory from scratch. He had no idea of Schwarz, Klein, Riemann, etc. And then, of course, he created this theory, and then he called it Fuchsian theory because of that. So he invented this concept of Fuchsian group, Fuchsian functions, etc. And as I told you, all this creation of Poincaré was done in the context of a competition for the Academy of Sciences in Paris. And this competition was totally anonymous. So during 1 year, Poincaré was sending drafts and papers to the Academy of Sciences without putting his name. It was putting a Latin motto. So nobody could know that this was Poincaré, except that it seems to me that, first of all, the handwriting of Poincaré is so recognizable that it is clear that Hermite probably knew that Poincaré was behind this competition. And so Poincaré was totally disconnected from the rest of the world, and he was producing these papers on Fuchs, etc., Fuchsian equations. And then when the competition was finished, and then when Poincaré did not win the prize, Poincaré began publishing official papers in the compte rendu. So he was publishing papers, which were now under his name and open to the world. And the world means Felix Klein. And so this is why Felix Klein wrote to him in 1882. In 1882, Felix Klein wrote to him explaining to him that somebody called Riemann existed, etc., and complaining that Fuchs was not connected at all with that. And Klein said you should not call that Fuchsian group. In Germany, we are used to disconnect mathematical concepts and human beings. So you should call that automorphic group or automorphic functions. And if you really want to put a name, please put the name of Schwarz and do not put the name of Fuchs. But the poor Poincaré already was linked with Fuchs because he had used the name Fuchs, and of course Fuchs was very satisfied to have his name connected with that. So Poincaré said, I'm sorry, I cannot change my terminology now because, what would it be with Fuchs? And then Poincaré made a big mistake because the next step for Poincaré was to write a paper in which he invented functions which are not invariant under a subgroup of PSL2R, but under a subgroup of PSL2C. And then he decided, as a compromise, to call them Kleinian groups. But then Klein was really upset with this terminology because he said he had nothing to do with that. And then he wanted Poincaré to withdraw this terminology. But again, Poincaré had published papers on the question. You have to know that at the time, for example, in 1881, Poincaré wrote 27 papers that year on this topic. That means that papers were received, accepted immediately, nobody could read them. Anyway, nobody except Klein could understand them because they were really badly written. So it was too late for Poincaré, and the name Fuchsian and Kleinian remain today, and there should be, of course, Schwarzian. But this is too late now. Okay? So that's a complicated story, difficult to understand, and I try to explain this. Okay, so let me begin by this idea of Poincaré. Step number 1, I want to construct examples of groups. Step number 2, for each group, I want to construct some automorphic or Fuchsian function. And step number 3, for each group, I want to construct an algebraic curve. So, first step is to construct examples of groups. So I should say step 0, which is really actually a major step, is really the discovery by Poincaré of the Poincaré disk and the link with hyperbolic geometry. So it is really amazing that all these people, like in particular Schwarz and Klein, they of course were aware of the existence of hyperbolic geometry, because hyperbolic geometry has been discovered by Bolyai, Gauss, who else? All these people knew about hyperbolic geometry. They knew that. But it is amazing that only Poincaré observed that holomorphic bijections of the disk, which are really, we know the form, this transformation like that. Coincide with isometries of what we call today the Poincaré metric. So that was the observation of Poincaré. And really, again, it is amazing that people like Schwarz did not realize that. Maybe I should put a plus here, orientation preserving. So what really Poincaré understood is that if you look for Möbius transformations preserving a disk, well, these Möbius transformations are actually isometries of some geometry, which turned out to be the Lobachevsky plane, what we call today Poincaré disk. So Poincaré is definitely not the discoverer of the Poincaré disk. It was known before, but he understood this isomorphism between the holomorphic structure on the disk and the isometry and the Riemannian metric on the disk. Note that historians have no idea of how Poincaré, it seems that Poincaré, even though he was not discoverer of hyperbolic geometry, he was not aware of that. I mean, he was not consciously aware of that some people did discover hyperbolic geometry before him. He just discovered it, and that's it. I mean, it is at that time a very small number of people understood hyperbolic geometry. There is a famous letter of Hermite to Poincaré. Hermite writes, I told you, 27 papers in 1 year. Of course, he sends them to Hermite. Hermite was the guy in the academy taking care of his papers. And there's a letter from Hermite saying, my dear Henri, my dear Poincaré, okay, I will publish your paper, but I don't understand a word about hyperbolic geometry, and I'm not sure it's correct. So even at the time, the same year, 1881, the head of the Academy of Sciences in Paris had proved the fifth postulate of Euclid and had published a wrong proof of the uniqueness of geometry. So at the time, you have to know that even the best mathematicians, some of them knew that hyperbolic geometry was consistent, but some of them did not believe it was correct. So you have to, that's true, you have to be careful. At the time, people were just, it was unclear. And it is very interesting to see how Poincaré is describing this geometry himself in his paper, because he don't want to be, he doesn't want to be aggressive with the academicians. So instead of saying hyperbolic geometry, geodesics, points, etc., he explains in the introduction this is just a matter of convention. He's using words that just suggest analogy with something, but in practice, when he says geodesic, he really means a circle. But this is for the convenience of speech. So he takes a lot of care not to be in conflict with the people in power of the time. So that's step number 0, which already is very interesting. You know, it's this famous story that Poincaré understood this isomorphism just by stepping into the bus. He was in a geological excursion. He took the bus. He entered the bus, and he explains that immediately he understood that. And then it was clear to him that it could be used for step number 1, 2, and 3. So let me go to, I don't want to say more about that because I think today, I hope most of you know what hyperbolic geometry is. And this was not clear at all at the time. So let me begin this step number 1. So the idea of Poincaré is this. Let me just give the simplest case. You take the Poincaré disk. So for him, it's the unit disk. And I take the simplest case for us today, but it's not the simplest case in his case, in his situation. And you take a polygon with 4G sides. And you assume that you label them by letters like A1, B1, A1 inverse, B1 inverse, A2, B2, A2 inverse, B2 inverse. And you assume that the labels, the sides with the same label have the same length. So you assume that the length of this is equal to the length of that. The length of this is equal to the length of this. Length of this equal, etc. Length, of course, with the Poincaré metric. Then you consider the isometry of the Poincaré disk that maps A1 to A1 inverse. You call it, let's say, A1. Then you look at the isometry B1 that sends B1 to the other copy of B1, and you have, in this way, you have 4 isometries, A1, B1, A2, B2, which are elements in PSL2R. So they are just the isometries that glue the corresponding sides. And then you want to consider the group gamma generated by these 4 elements. And you ask yourself, do I generate a group that will have this polygon as a fundamental domain? The group will act on the disk, and I wish I could get a group for which this polygon is a fundamental domain. Then Poincaré notes that there is a necessary condition for that if you look at the angles, the interior angles, if you want that after this gluing you get something smooth, then the sum of these angles should be 2 pi. So you have to have this sum of the angles is equal to 2 pi. And then you have the theorem of Poincaré that under these conditions, indeed the group generated by these four elements is a Fuchsian group. Meaning that it's a discrete subgroup of the full group of isometries. As we would say today, the quotient of the disk by the group is a surface of genus 2. But I told you Poincaré does not say that. But Poincaré says the polygon is a fundamental domain. So what does that mean for him to be a fundamental domain? That means that if you take 2 points in the interior of the polygon, they are not in the same orbit of the group. And if you take any point in the disk, there is some element of the orbit that intersect the polygon. It will be unique if the point is interior, and if it's not in the interior, for example, if you have a point here, then the other elements in the same orbit are on the boundary of the polygon. So he makes this very explicit. So you have to prove something. This is a real theorem. And in order to show you that this is indeed a real theorem, in the first paper he presents this. He gives no proof because he says it's clear. Then he gives a wrong theorem. Let me show you why. Poincaré is not only interested in compact Riemann surfaces with finite polygons and a finite number of sides. He looks at the following example. You consider the disk, and you say 4 points on the boundary, and you take a quadrilateron. Then you might say, I take an isometry. Let me call it bad notation F. I take an isometry sending this geodesic to this geodesic, sending gamma to delta. And I take an isometry sending alpha to beta. And exactly in the same way as we had here, Poincaré claims that the group generated by F and G is indeed a discrete subgroup and the quadrilateron Q is a fundamental domain. And this is wrong. This is not true. So let me show you why it is not true. This is Poincaré's mistake, and Poincaré theorem there is this compact version is correct, and this non-compact version is incorrect because some argument is missing, some necessary condition is missing, and of course Poincaré will understand his mistake maybe after 13 or 15 papers, and will correct the mistake later on. But in the first paper he claims that this is not correct, and here's the reason why this is not true. In modern terminology, well, if it were true, that would mean that the quotient of the disk by this group, would be a sphere minus 4 points, because you have these 4. Am I right? Will be a torus. It will be a torus with minus 1 point. It would be something like that. Okay. And this element here is, of course, the commutator. And since you see here a cusp, that would mean that this corresponding element as an element of PSL to R should be a parabolic element. Its trace should be equal to plus or minus 2. And of course, there is no reason that this should be true. You see, if you have F and G satisfying that, you can find another F by taking the previous F, composed with any map, any isometry fixing these 2 points. And the group of isometries fixing these 2 points consists of hyperbolic elements moving from there to there. So if you change this f by post-composing it with a hyperbolic element having these 2 fixed points, you will really change this commutator. And this commutator has no reason to be parabolic. It will change, and its trace will change as a function of the power of the hyperbolic element that you use here. So in general, it is not parabolic. So in general, what you get when you take the quotient of the disk by this discrete group is something like that. And it took time to Poincaré to understand it. You get a Riemann surface with infinite area. And this Riemann surface with infinite area, of course, cannot have this polygon as a fundamental domain, because this fundamental domain has finite area. It consists of 2 triangles. Okay? So what turns out is that if you take this polygon and if you take all its images by the group, they will tessellate not the full Poincaré disk, but a part of it. Which part? The convex hull of the limit set. So let me, you have a closed geodesic which appears on this non-compact surface. If you go to universal cover, this is the Poincaré disk, you will have this closed geodesic will lift 2 collections of geodesics like that. And what's left is a convex set and this green area is exactly what is covered by this quadrilateron plus all its transformed, all its images by the Fuchsian group. So when you begin tessellating the Poincaré disk, you put copies of the polygon, and they are not going to the boundary. They are converging to these closed geodesics, and they will only tessellate the universal cover of this convex core. Okay? So really, if you want to prove the correct statement of Poincaré theorem, you really have to impose that for each cusp in the corresponding Riemann surface, the corresponding commutator is parabolic. Is that clear? And again, initially the proof of Poincaré was not correct, but he understood that. And when he understood it, he corrected it, and the final statement and proof is correct. Okay, for the statement? What? If the commutator is parabolic, then it's correct. Okay. So the correct statement of Poincaré theorem is, you start with a polygon with a finite number of sides, some of them going to infinity, some of them not going to infinity. You assume that the sides are an even number of sides, and you glue them 2 by 2. So you assume that so there is an involution in the set of sides. So this one, alpha, is identified with this side. You want, of course, the sides to be identified to be of the same length. if you have an infinite side, you want to go to an infinite side. So you assume that the sides are paired 2 by 2. You assume that the sides which are identified have the same length. And then you put two conditions. First, you put an angle condition, that the sum of the angles at the corresponding vertices will be correct. And then you put a trace condition, a parabolic condition, at each of the cusps that you want to create. And then the theorem is, if these necessary conditions are satisfied, if you take the group generated by these elements that you have, identifying sides, then this group will be discrete, and the image of the polygon by this discrete group will cover the full Poincaré disk and will give you a fundamental domain. Okay, so this theorem is correct, and this, I will not prove it, but this is now very standard. It's found in any book on Fuchsian Kleinian groups, and the proof is clean today. I just wanted to go to the history of the theorem. Okay, so that's step number 1. Now, let me also mention a mistake, another mistake of Poincaré, which for this time is a serious mistake. Poincaré makes the following comment or statement or claim, which is true, but for which he has no proof. The statement is this: if gamma is a subgroup of PSL2R, discrete, so a Fuchsian group, generated by a finite number of elements, then it has some fundamental domain which is polygonal, some polygonal with a finite number of sides. So it is clear for Poincaré that if you start with a group which is finitely generated and discrete, it has some polygon, maybe with vertices at infinity, which is a fundamental domain. This is true, but it is not easy to prove, and it was not proved until the 1960s. The fact that this is non-trivial is expressed by the fact that if you go higher dimension, it's not true. If you take a finitely generated group of isometries, a discrete finitely generated group of isometries of the Poincaré ball, dimension 3, if you assume it's just finitely generated and discrete, you could say, does it have a fundamental domain which is a polyhedron, whose faces are limited by totally geodesic planes? And then the answer is no, it is not true. Some discrete, finitely generated subgroups of PSL2C do not have a fundamental domain which is a polyhedron. The name is, what's the terminology for that? Some which are called wild Kleinian subgroups are not like that. They do not have polygonal things. So for Poincaré, he doesn't even mention this question. It's like it's a mistake. It's a mistake. But this is true. This is. Okay, now let me now go to step number 2. how to construct, given a group gamma, given gamma, a discrete subgroup of PSL to R, and again, step number 1 enabled Poincaré to construct many examples. Just take a polygon and just take the group generated by that. How can I construct a Fuchsian function? So it's a function from the disk, which is a meromorphic function. And which is invariant under the group. So, again, Poincaré mentioned explicitly what he's trying to do is to mimic the theory of elliptic functions. So you're given a lattice, and you look for something like a Weierstrass function that will tell you it's a meromorphic function which is defined by some sum of something which is clearly invariant under the group. So he wants to mimic this. And this is where he creates the concept of Poincaré series. Poincaré series. So here's the trick. Well, you want to construct something which is obviously invariant under the group. So his idea is to take a sum. So here's the idea of Poincaré. You choose some rational function of Z. Rational function in one variable. So the quotient of two polynomials. And then you define f of Z to be the sum over all elements of the group of f of R at the point gamma Z. That would be great, but that would be a sum which is, of course, invariant under the group. But, of course, there is no reason that this series is converging, because the general term will not go to 0. And then you modify this by taking here the derivative of gamma at Z raised to a power k. And the fundamental lemma, you will see the proof is really wonderful and clear, I hope. The fundamental lemma is, of course, this function is not invariant by gamma, but the function is if k is at least 2, then this function f, this series is converging. So this function f is indeed well defined if k is big enough, if k is at least 2. And if you have that, I will explain the proof. Of course, if you compute f at a point gamma z, well, it is not equal to f at z, but you see by the chain rule, you have a term which goes out. So what you really have is that f at gamma z is just f of z multiplied by gamma prime of z to the k. So this is what we call today a modular function. It's a function which is not invariant by the group, but which defect of being invariant is controlled by this derivative. In modern terminology, we would say that f is not invariant, but the differential form, f of z dz to the k, as a section of the kth power of the canonical divisor, we would say today, this object is gamma invariant. This is the modern terminology. Anyway, that's obvious by the definition. Now, this is not what we want. We want a function which is invariant by f. Okay, so then you note that this function f depends on the choice of rational function r. Then the trick is very simple. You take two functions like that and take the ratio. Now define f of z to be equal to the ratio of these two functions put for two rational maps. It is clear that f is invariant under the group because, both satisfy this function, hence the ratio is invariant. Now the problem is, how can I make sure that this function is non-trivial? Well, let me make a comment on that. Using, again, modern terminology. Suppose, instead of rational map, I choose a polynomial. Suppose R is polynomial. Then this function fr of z is not only meromorphic, but is holomorphic. So this is holomorphic form on the quotient d mod gamma. Now assume this quotient to be compact. So now we know from the modern theory of compact Riemann surfaces that the vector space of holomorphic sections of the kth power of the canonical divisor, in other words, the space of holomorphic forms of this shape on a given Riemann surface has finite dimension. So this space has finite dimension. And even using Riemann-Roch theory, I could compute this dimension, computable, as a function of the genus and k. Anyway, given the genus, given k, this dimension is given. But the space of polynomials is infinite dimensional. So you have an infinite dimensional vector space of polynomials. Each one gives rise to a smooth holomorphic k-form on a Riemann surface. You have a map, a linear map from a vector space of infinite dimension to a vector space of finite dimension. So it has to have a huge infinite dimensional kernel. In other words, for many polynomials p, for many p, this is identically zero. And I have to say that still today is kind of a mystery. What are the polynomials p? I give you a Riemann surface. What are the polynomials p for which this is equal to 0, identically? It's not non-trivial. It's a complicated question. So this is just to mention that it is not clear at all that this function is non-trivial. There might be a general theorem that is always 0. Okay? And the trick used by Poincaré to produce examples for which this is non-trivial is a very, very simple observation. Choose R, the rational map, for example, having a single pole in the fundamental domain. having a single pole in a fundamental domain. In, let's say, even in the disk. For example, choose R of Z is 1 over Z minus Z0, where Z0 is some element in the disk. Well, you see that when you choose this rational map, and when you compute FR of Z, which is by definition the sum of R at gamma Z, gamma prime of Z to the K, so this is the sum of 1 minus gamma Z well, explicitly you see that this has a pole at Z0 and has a pole at all points in the orbit of Z0. Since this function has a pole, it's not zero. A function which has, I can even compute the residue at the point Z0. It's 1. Okay? So this function is indeed meromorphic. Has a non-trivial pole at all gamma Z0 for all gamma in gamma. And we only use that to say, hence the function is non-trivial. Hence, FR is non-trivial. Now you take two different Z0s and Z1s. You get two functions which are meromorphic functions having poles, so the quotient cannot be a constant. So this function is not a constant. And you see you have a lot of flexibility to construct examples which are not constant because you have the freedom of choosing poles wherever you want. And this constructs many, many Fuchsian functions. That's a very simple idea. Okay, now I have to prove this. And you will see that this is really the place where hyperbolic geometry makes it obvious. And using the terminology of hyperbolic geometry will transform this in something completely obvious. Yeah.
Is there like a geometric picture to this construction? That you have this function, your function that's going to the sphere.
Yeah. It's
pole at a certain point to the zero. Like, is there a way to, from this formula, to see a picture of how it's being constructed?
So you asked me a question. Let me ask you a question. What about the corresponding question for elliptic functions? When you have the definition of the Weierstrass function by like an infinite sum, it explicitly writes the elliptic curve as a branch cover of the sphere. Do you see that geometrically? So this is the same question. It's transcendental part of the proof. This is a Weierstrass point of view, and therefore non-geometrical. Okay, so I want to prove this lemma. And of course, the derivative, if you have gamma of z is az plus b, cz plus d, derivative gamma prime of z, as you know, is 1 over cz plus d squared. So if I want to compute, if I want to see that the series sum of r of gamma z, gamma prime z squared, gamma prime z to the kth power is converging, I just have to find a good estimate for the velocity at which this goes to 0. I want to show that this gamma prime to the kth power goes to 0 very quickly. So quickly that this series is converging. So the idea of Poincaré is that at least there is something which is obviously converging, and this is the geometrical idea, is that if you take your disk, you have your fundamental domain, you pick a point, and you take a ball of radius epsilon around it. The ball is a ball in the Poincaré sense. It's a ball in the Poincaré distance. And you take the images of this ball by all the elements of the group, and of course they will pack inside in the disk. They will be disjoint 2 by 2 if epsilon is small enough. Because the group is discrete and fundamental domain is domain. So one thing is completely clear, is that the areas of these disks give a converging sequence. So geometrically, it is completely clear that if I pick a point, say Z0, it is clear that the sum of the areas, of course areas in the Poincaré meaning, of the images of this little disk is converging, where delta is this disk of center Z0 and radius epsilon. And then the trick is to say that, of course, these, I'm sorry, I said something stupid. Areas in the Euclidean sense. Yeah, of course, Euclidean areas. Because you have disks which are packed in a disk of total area pi. They are Euclidean areas. Of course, the hyperbolic areas are all equal because one is the image of the other by some element of gamma. So the hyperbolic area here and here are equal. So the series of the hyperbolic areas is diverging because it's a constant series. And now the trick, of course, the Euclidean areas are, I'm sorry. Okay. And now the idea is to say that, well, the Euclidean area of gamma of delta is of the order of gamma prime of Z naught squared. And why is it so? I mean, it should be clear. Well, let me give a rough idea of the proof, where you take this little disk, you map it by some element in gamma, you get a small disk here. Of course, this image of the disk is another disk, but the center is not quite gamma Z0, and the radius here is not quite gamma prime of Z times epsilon, but it is of the order of. It's a conformal map, it's a Möbius map, sending this disk to this other disk, and the radius of the image of the disk is, roughly speaking, the radius of the original disk multiplied by derivative of gamma. So roughly I can say this, that the area of the Euclidean disk gamma of delta is of the order of the derivative at Z0 modulus squared. Modulus squared. Okay? So if this is correct, you see that this series is uniformly converging if k is at least 2. That's the proof. Then you have to fill details that I don't want to do because it's boring, but it's really easy. You just have to show that indeed the Euclidean, you have to show that indeed, I'm right here, the Euclidean radius of gamma of delta divided by the hyperbolic divided by gamma prime at z0, this ratio is bounded above and bounded below by some constant k, 1 over k, and k is a function of z0 and epsilon. Now, this is a very simple exercise to make this quantitative. Okay, so this is the basic idea for step number 2. Now let me go to step number 3. I remind you, I'm given a group, and you have this polygon construction that gives you many examples. With the group, I construct many Fuchsian functions, which are invariant under the group. And step number 3 is any two Fuchsian functions are linked by some rational function, by some polynomial equation. So they define an algebraic curve. So let me go to that last step. So the last step. Any two Fuchsian functions f and g for the same group, of course. So f and g from the disk to C infinity. Satisfy P of fg is equal to 0 for some polynomial P, for some non-trivial polynomial P. In other words, any two functions define an algebraic curve, and this algebraic curve is well defined up to birational equivalence. So the proof of that, I will give it to you now, is easy, and I think should be attributed to Riemann. Even though, of course, Poincaré rediscovered it, as I mentioned to you. So here's the proof. Let me express it in modern terminology. I should say, should I? Oh, okay. I assume. I need some compactness, of course. So assume that a compact fundamental domain. So in modern terminology, that means the following. You have the disk, you have two functions f and g, and both of them are invariant under the action of gamma. So we think this way. The quotient is a compact Riemann surface. And on this quotient, we have two maps. Let me call it again f and g. On a Riemann sphere. C union infinity. And I want to show that they are linked by some polynomial relation. Well, it's very easy. You do the following thing. You pick a point here, You take its pre-image. Well, you have a finite number of points. And you take the images by f of this finite set of points. You get a finite number of points in CP1. So for each point here, let me call it x, I can define some kind of finite collection of points. Pi of x is a finite collection of points in CP1. So that means that for each point in x, I have not one point, but I have a collection of points. Of course, there is no canonical way to order these points from the first to the last. So what you do, since you have no ordering, is that you take symmetric functions. So for each x, you define, let's say, sigma 0 of x, sigma 1 of x, to be the sum of the elements in pi of x. You have a finite collection of points in C union infinity, you sum them. You define sigma 2 of x to be the sum of the 2 by 2 products of elements in pi of x. And then you go to the last, if you have, let's say, k elements, sigma k of x to be the sum of the k by k products of elements of pi of x. Of course, you have first to prove that the cardinality of this set is constant as a function of x if you count multiplicity. But that's very easy. And of course, since I'm using functions which are invariant under the symmetric group, these are well defined. I mean, I don't need an ordering to find the sum of the elements. I don't need an ordering to take the sum of the products 2 by 2. So these are really well defined. And then, well, I'm finished because now all these functions sigma I are meromorphic function on CP1. Are meromorphic. Now, this should be checked at infinity, etc., but this is no problem. And we know that a meromorphic function on CP1 is nothing more than a rational map. So we know that sigma I x is pi of x divided by qi of x, where pi and pi are polynomials. In one variable. And now I hope this proof is finished, because that means that if I know the image, if I know the value x of g, I do not know pi of x yet, but I know all symmetric functions of its elements. Therefore, I know it, because I know the polynomial having this as roots. So then I have, so the consequence of that okay, the consequence is that I take a point here, any point. How can I call it z? I look at x is f of g z. I look at y is f of z. So y is some element in this finite set. X is this x, z is here, okay? And I know that y is one of the roots of the polynomial yk plus sigma 1. Maybe there's a sign somewhere. Okay, if I know the symmetric functions of a finite set of points in the complex plane, I know the polynomial having this as roots is probably, there may be a wrong sign somewhere, no? Yes, it's minus. It's alternating sign. Eh? This is the Newton formula, for not even Newton, I mean, Viet formula or something, given the symmetric functions of the roots of the polynomial as a coefficient, as a function of the coefficients of the polynomial. Okay, so each time I take any point z on the Riemann surface, I take its two images by f and g, I have this polynomial vanishing on x and y. So if I call this polynomial p of xy, I did prove that p of g and f is identical to 0. So indeed, and this again, this is, I think one finds this explicitly in Riemann thesis. Any Riemann surface has the property that any meromorphic function on it are related by some polynomial equation, and the proof is this. And again, Poincaré found it before he knew about Riemann. Okay, so let me just give a summary of what we did today, and then what we are going to do next time. So today, I remind you that our goal is to prove some uniformization theorem that, for example, the universal cover of any Riemann surface of genus 2 or more is the Poincaré disk. We are not doing that. What Poincaré did, and this is before he thought such a theorem could be true, was going in the opposite direction. You start with the Poincaré disk, you begin proving that you are able to create many groups acting on the disk, you take the quotient, and you show that this quotient is indeed an algebraic curve. So this seems to be totally nonsense, because you go the other way. Instead of starting with an algebraic curve and trying to uniformize it, you start with some uniformization, and you find an algebraic curve. This looks ridiculous. Then you have to prove, and this is what we are going to discuss next time, you have to prove that you have enough parameters in the space of your constructions to construct enough algebraic curves to get all algebraic curves. And this is the next step, which will be the hardest one. We have to prove that indeed the map going from groups to curves is one-to-one, that's easy, but onto. And if it's onto, we will have the uniformization theorem for algebraic curves. Any algebraic curve will be uniformized by some group, some Fuchsian group. Okay, so we are really half the way, or even not even half. We did 1/10 of the way, because we have only constructed examples of some groups which create some algebraic curves. We need to prove that we got all curves. And this is the meaning. We have a quote of a friend of Poincaré. He was a fellow student of him in École Polytechnique. And he wrote that on December 31st, 1881, his parents invited Poincaré for, having a New Year party in their home. And Poincaré was there, and he was not saying a single word. He was not taking part of the fest. He was not taking part of the celebration, and he did not even notice that it was midnight. So the friend says that at some point he had to say to Poincaré, you know, Henri, now we are in 1882. And Poincaré was, according to the letter, was outside of the world. And Poincaré said to his friend, I know how to solve all differential equations. So this is what he said. So it seems that exactly on December 31st, 1881, at midnight, Poincaré understood that there was some hope that this map from groups to curves could be a bijection. Okay, so the proof will be long, and probably I will not go into details, just give a rough idea the way it was working, but I will try to go to that point next time. Okay, thank you.